Oh, hi Peter.
How are you?
Everything is okay. Busy
Yeah,
as usual. How about you?
quite well. It has been some time,
Yeah,
but
it's been a while.
yeah, but since we talked last, I've been looking a little deeper into to new motor technologies, and I found the axial flux motor as a it seems to be a newcomer, but I know you have been working within this topology, and therefore I called you because I would like to learn a little more about axial flux motors.
Okay.
Can you tell something? Do you have something you can show me? Because
Well, it's
I really need to learn a little more.
it's not something super new, I have to say. Like, yeah, give me a second and I look because I've some slides from a seminar or something that I can try share it with you.
That'll be nice.
You see my screen?
Yeah, you on?
Yeah, so, okay, I mean, this is like, for example, just to give you an idea of where the axial flux technology starts, like
Yeah,
this is an interesting fun fact because
yeah.
this
And
presentation is made like also for students, and
uh,
like this year we went to visit with them a power station, one of
uh,
the very first power station in history, to be
yeah.
honest, and so on.
Okay.
And
How old is that?
this is belonging to the late 1800s, so 17th
Hmm.
century. And you see, like
Yeah.
these machine are the first
Wow.
machine of ABB, like
Yeah. Oh,
big
can you put
pieces
in
of history.
presentation mode? It's a
Oh
ooh,
yes.
then I can better see it. Fantastic.
So this was an hydraulic power station, and interesting is that I asked the student to focus on something because on the basement of the power station there was this piece. Okay,
Yeah.
this piece of antiqueness, but it's a very peculiar things because I was making them focus on the fact that this is actually an axial flux motor. Okay, and
Yeah.
so everybody thinks that right now that axial flux is kind of a new technology. Okay, like
Mm.
something very fancy and new, but at the beginning of when the electrical machine technology has been developed started, the axial flux machine was actually being exploited, okay? And this is a piece from the late 1800th century, but I'll come back to it because right now we are not going very far from it. So basically, the
Okay.
concept is there, was there since a lot of time.
Okay. And it's quite big.
Yeah, it is quite big. And the point is
Mm.
that, at that time they didn't have finite element or all the technology that we have. So it's actually a very heavy piece of equipment,
Yeah.
It's made of solid steel. So it's like, yeah, it's
Wow.
quite an interesting
Mm.
it's interesting structure, so
Yeah.
somehow.
Mm.
But
Uh, but what has happened since?
yeah, but what happened since? It's happened since that we preferred radial flux, but like for
Mm.
example, for explaining what is an axial flux machine,
Yeah.
usually I refer to these pictures that has been made by colleagues, but they actually explain very well that the concept because there is not much difference between a radial flux and an axial flux apart the flux direction. Okay, the
Mm.
concept is all there. So if you take a radial flux machine, you cut it and you
Yeah.
stretch it, and you stretch it also from a tangential
Yeah. So you open
perspective.
it up.
You open it up, basically.
Yes.
Yes, you achieve basically you can switch it from an axial flux to a radial flux machine. So these Dubas and Kuo and so on, they've done this nice analysis where you can actually transform, okay, one radial flux to an axial flux through the equations, and it's a very interesting concept to open up your mind and not constrained to the radial flux topology, but
Mm.
so nothing. you know, like the technology has been all there and the concept has been all there. And yeah, but if you, when you discuss about axial flux machine, you know, like there are many other degrees of freedoms that open up in terms of the capabilities. And so, for example, how I like usually to consider and make my students think about the fact that when you talk rotor and stator, in axial flux, usually you can go like with this matrix shape structure where you can have ferromagnetic cores that are both on stator and rotor as this this structure, but you can also work on coreless structure where you have, for example, in this case, stator PCB, or here you have an ironless rotor structure, and or in such cases where you can use, for example, here they have epoxy rotor core with permanent magnet embedded in it, and an ironless structure. So.
But the stability or the mechanical integrity of that must be a little hard.
It is. It is actually. It is. It is very challenging as a machine from ferromagnetic perspective. Yes, because you need to consider a 3D flux path, and therefore, you know, we need to go on 3D finite element or on analytical models that take into account the 3D shapes and so on. And from a mechanical perspective, yes, because it's a disk, and therefore disk have a completely different stress and rotor dynamics response from a mechanical perspective, and therefore, yes, they require much more in-depth analysis and consideration. You need to consider the technology for what it is and go in depth analyzing it. But they have also benefits. They have also benefits. For example, you can actually use multi-stage. You know, I think that yeah, for example, you know, if you need to increase powers and so on, you can actually design a single stage. So you target a machine and then you stack a lot of them, one on a side, to further exploit the axial length of the structure.
And is it just multiplied in torque level with the number of rotors?
Yes, basically, you know, they are all on the same axis. So they have one single rotor, one single shaft with different discs applied to it. Somehow resemble a turbine, a jet engine. Okay, if you consider it, and therefore all the rotor dynamics problem of jet engines and so on comes here when you design it, when you consider it, and so on. So yeah, it's a very interesting topology to be exploited. Also, again, it opens degrees of freedom. Another degrees of freedom, you know, that comes to my mind. I think that I have some support here. Yes, like it's coils, you know. Like usually in an electrical machine, you discuss about concentrated radial flux machine. It's like concentrated or distributed winding and so on. Here you can actually rearrange the coils in a different way. So for what is more suitable for your let's say application and so on, and also to exploit the multi-physics, cooling and so on. I think we discussed a few times about you know, these property, these capabilities to further exploit with in technology. So yeah, there are like many ways of arranging this machine. But usually, you see here, there are many of these machines are permanent magnet. You see, like permanent magnet is something that is
it's the standard to have permanent magnets
for high power density. Okay.
Yeah.
But these machines, they are very interesting also when you start exploiting the anisotropy of the structure. Okay, so you go to switch the reluctance. So basically, you use the variation, of reluctance in order to produce the torque. And you see, look at this picture. You see,
so every second. So you have every second pole is just iron.
Yeah. But the figure 5 here is very similar to what we've been seeing on the other structure. Okay.
Yeah.
you see the problem that one of the problem why this technology has not really spread everywhere like radial flux machine is because radial flux machine exploit a lot what is like laminations, okay?
Yeah,
So
okay.
electrical steel sheet, and
Yeah.
in this case,
To cut these laminations must be very difficult or very costly.
very
And
costly. Yeah.
and assembling them afterwards, it must be a mess.
It's not an easy task. I think that's one of the things that is making this technology like not so widely available and so on. And also, it is costly, and usually these type of laminations are being developed in order to drastically reduce the losses. Okay, when you have a radial flux path, where for axial machine the flux path is not exactly easy to configure and determine. Therefore, you need grain oriented or you need structures and so on. So losses are quite a critical thing. That's why some people, like there is research, a lot of research on coreless design. Okay, you reduce a bit the capability of your machine, not including iron, so you lose in some way from electromagnetic point of view, but you also lose the losses. Okay, so they are playing with this. Okay, and like the topology that you can play and the structure you can have when you open up the degrees of freedom of three-dimensional path are multiple, variegated, like single poles that are iron, this shaped stator structure, C-shaped stator arrangement. This is a concept that Professor Bolognesi a few years ago conceptualized. Is basically a modular switch the reluctance machine. So like you can play a lot with it.
Yeah. But what sizes can you do? Some of them seems quite small, but the one you started with from this the water turbo machine was quite big. What is the sizes you do today?
Well, today you can find a very wide range of sizes. So and also size of application. The phone application and in very different types. Like I think here, yes, I have like for example, look at the size of these species, like tidal energy harvesting, and it's quite big. We are talking about meters, okay?
Yeah.
Meters of
and here the motor is in the outer ring?
Yeah, it's basically in the outer ring. Yeah, you see here the structure, okay?
Yeah.
The stator magnetic circuit and so on. And but automotive is basically right now also considering axial flux quite a lot. These are just three.
Yeah, I know these names.
Yeah, I think yes.
The one in the middle, it's still on my Christmas wish list.
Yeah, they've played a lot because they allow you to achieve actually very high torque density if you arrange cooling and the structure, compactness, and therefore for automotive is quite an interesting and attractive solution. This can be used also for direct drive application. This topology, it resembles the shape of a wheel, right? So some of them can be also considered to be actually inserted in a wheel itself, embedded in a wheel. So there is a lot of flexibility that they can give you.
What about speed? Some of these applications, the tidal wave application must be quite low speed.
Yes.
So how is speed and torque varied? Can you go very low speed, extremely high torque with these machines?
Yeah, I mean, the speed issue is a very interesting topic for this machine because these machines that you are watching here on this slide are going quite at high speed. Okay, when we discuss a high speed, we also need to consider the fact that when the limit of high speed in a, well, let's say, the threshold of high speed in an electrical machine for me is always been not the RPM, but the peripheral speed. Okay, so since you are using an axial flux and therefore you're spreading your material in the axial direction, so the radius become big, the peripheral, so the tip speed actually increase. Okay, so the stress on the material become quite important. And also from the rotor dynamics aspect, you know, if you look any book of rotor dynamics, they actually distinguish between beams shape or disc shaped, because they have a rotor dynamic behavior that is actually quite different. Okay.
And so on torque level, this also seems quite big. 800 Newton meter.
Yes.
It's a machine that I cannot hold it in my hands.
No, it is like, it is very, very, the torque density is also basically due to the cooling structure, okay, because you can increase, you can push current in coils, let's say as much as you want, if you have a cooling system that allow you to push such a current through without burning it, so to say. Plus, you know, there is another interesting thing that you see here. Okay, somehow, you know, in a radial flux motor, usually the end winding is lost somehow. You know, they don't produce, they don't engage in torque production somehow.
It's what I try to show on my back, the picture where on this side you can see the end winding, and on the other side the end winding has disappeared because we have shrunk the height of the bridge when we work with SMC materials.
Exactly. And somehow the axial flux machine somehow has embedded that feature, which can be further exploited. Okay, so if you have a smart design, you can actually really fully exploit this capability. But somehow the axial flux has already embedded it that the end winding is not really completely lost as copper. So you actually exploit better the copper you put, and the copper is expensive, as we know. So but again, you know, like this, look at the size also of the application. You can go here very low speed. So the critical thing is not about.
Wow. So this is for a windmill?
Yes.
Wow. It's quite big.
It is quite big.
What power level are we at here?
I think is on the megawatt range. Okay.
So it's a real size.
Yes. Yes. So for example, if I go back a second, you know, we are going from this application that this is a megawatt scale, kilowatt scale, megawatt scale. If you look at this application, these here, okay, epoxy rotor and so on, these are very niche application, okay, very small type of application. For example, I've seen this topology used also in biomedical applications. For example, you know, you go small and you go for circulation, for example, of blood inside human, and so
it's few watts.
Yes.
Like few millimeters or centimeters in size. Okay.
So it's very scalable.
Yeah.
I think that what I mean, it's a summary. You know, okay, you know, if you consider the axial flux, you know, like you see here, you can go from kilowatt to megawatt. You can scale it up. So you can go from centimeter, like as you're saying, really tiny pieces, to really meter diameter, 5-6 meter diameters. You can reduce the mass, the active mass that you want. For example, going coreless, but there are other way of reducing mass with respect to radial flux machine. The copper value is maximized with respect to radial flux. you can consider direct drive system, like again in wheel or other ways, and
So
they provide
yeah,
high power density.
we have many motors with a gear for our conveyors in our factory. Could that be substituted one-to-one, a standard motor with a gear?
It could.
Also running at these low speeds, because that typically it's a standard motor that is geared down to like something like 100, 150 RPM.
Yeah. I mean, in terms of technology, there's nothing that stop you to go there. There's nothing to stop you to go there. In general, the problem here is about cost. Okay, but again, we discussed this before together that right now the electrical machine world has relied on electrical steel sheet, and the electrical steel sheet has an entire infrastructure around it to make it cheap. Okay, and it's not necessary through the best option. It's not necessary through the only way of doing things, and I think that the push for electrification is a bit making people rethink about different solutions. Okay, so again, in terms of possibility, there's nothing that stop you to do that.
Oh, yeah, I can see you have written on this slide, why SMC?
Yeah, because SMC, like the point is that somehow you rely on technologies that are nowadays available, but I open up the part of 3D part flux machine also thanks to Bolognesi that is helping me a lot to discover these things. But because the radial flux, the two-dimensional, usually finite element, B-dimension, and so on, has a lot of degrees of freedom. Synchronous, reluctance motor play a lot on barrier shape, and a lot of degrees of freedom. When you open up a third dimension, things got. Yeah, the possibility that there are really opening up, and it's very interesting from a university perspective to have the possibility to try to exploit them. Like plus modularity is something that right now in the world of of a world that is going this fast, having the capability of pick and place broken part is actually a critical aspect. Okay, also not to recycle components. Okay. Yeah, you don't lose the entire motor, but you replace the part that is broken. We are so much used to when something is broken, buy a new one. Whereas
okay, so if you have a segmented motor, you can just replace one segment.
exactly.
Okay. Yeah.
And plus, multiphysics, pushing power density. Why not integrate cooling? And when you have the capability of, for example, with SMC, that you can shape the structure as you want. You can actually make the path for air to flow, for fluids to flow, and share cold plates with power electronics and so on. So the possibility are quite a lot, in these terms. So SMC is something that is interesting to exploit in this sense. It's not the only thing that is actually interesting to study from an academic perspective, because there are many thermal aspects, again, mechanical aspect, manufacturing things. So there are many things and so on to consider.
Yeah, it's not always that easy.
No. But let's say that is interesting from a perspective to keep investigating those things.
Yeah. Wow. Yeah. Luca, do you have more?
No, I think I'm done. I think I was like here at the end of.
This
was just a general thing to make the students understand what are we talking about, and it's not something that should be scared of. I really like to start from here, because somehow we start from here and we arrive back to the same. So
I really like this. I have also been at some technical museums and seeing technology that we think has been invented over the last few years, but it's 100 years old, but was never measured at that time.
Agree.
Yeah.
I agree.
Luca, I have learned so much, and I have to confess, I have recorded our conversation.
Okay.
Do you mind if I share it? Because I think so many more people could learn from this.
No, it's okay. I could have said the wrong things, but I mean, we can keep discussing about these things and so on. But please share it.
You're
No
just
problem.
human, but you are quite clever human, so I don't think you said something wrong.
No
So,
problem. Share it.
yeah, wonderful. Thank you very much.
No problem. Have a
Uh,
nice continuation of the day.
yeah, you too. I'll come back to you when I have more questions for sure.
Okay.
Yeah, see you.
See you. Bye.